Hello friends, in this lecture we will discuss transportation. So transportation is another chapter in your syllabus under the quantitative techniques, and this is a part of the syllabus which is again easy to score. If you understand the concepts and you follow the steps prescribed, you can actually score well in these questions. This is again a chapter which mostly does come in the exam, so therefore please do pay attention to it. Let's look at transportation. So transportation is a mathematical technique used to minimize transportation costs of shipping goods from M factories to N warehouses. So from M sources to N destinations. So it is a process, or it is a technique of minimizing your transportation costs. What are the steps in solving a transportation problem? So there are 3 steps involved in transportation problem. The first is the preliminary check. The second is the initial basic feasible solution. And the third is the optimality test. So there are 3 things that you have to do to be able to solve a transportation problem. The first is doing a preliminary check. The second is finding an initial basic feasible solution, also known as IBFS, and the third is to do an optimality test. Let's look at the 3 methods of, so over here the second step, initial basic feasible solution, further has 3 methods by which you can find out the initial basic feasible solution. The first being the Vogel's approximation method, or VAM. This is the method that is most commonly used. If you get a question and nothing is mentioned, you should use this method. So this is the most commonly used, most important of the lot. The other 2 are pretty easy. So Vogel's approximation method, VAM. Second is northwest corner rule, and the third is the least cost cell method. We will understand each of these methods in detail, how to solve the problem under each of these methods. So now if we move on to doing a transportation problem or solving a transportation problem, we have to follow the 3 steps that we discussed. The first step being preliminary check. So what all do we check in before we start the initial basic feasible solution? The first thing that we have to check is that the problem given is a minimization problem. The objective is equal to minimization. If it is a maximization problem, then it should be converted to a minimization problem. So if it's a profit matrix, it should be converted to an opportunity loss matrix. And how do we do this? We do this by subtracting the highest number in the matrix. Subtracting all the values in the matrix from the highest number in the matrix. So the first check, preliminary check, is to ensure that your matrix or your objective is a minimization objective. If it is maximization, then we should convert it to a minimization by subtracting all the values of the matrix from the highest value in the matrix. The second check is to check whether the data is balanced or not. So what do you mean by data is balanced or not? The total availability is equal to the total requirement or not. If the data is unbalanced, then we have to insert a dummy row or column with all elements equal to 0 to make sure that our rows and columns are equal. So those are the 2 important preliminary checks. Checking the objective, it should be minimization, and the data should be balanced. So those are the 2 preliminary checks. Now let's get into the next step, which is finding out the initial basic feasible solution, IBFS. So there were 3 methods under this, and the first method was Vogel's approximation method, which is the most important of the lot, VAM. So Vogel's approximation method, what do we have to do here? We have to find out difference between lowest and the next lowest element of each row and column individually. So we have a matrix, we have rows, we have columns. What we have to do is we have to pick out a row, we have to see which is the smallest number, which is the second smallest number, and find out the difference and write it on the right of that row. The same thing we do for all the rows, and the same thing we do for all the columns individually. So for each row I will have a difference, I will have an amount of the difference, and for each column I will have an amount. So that is the first step, finding out the difference. Then I have to identify amongst the differences that I have written down, I have to identify which is the highest difference amount. So whichever is the highest, I put a box on it, which means I mark it, I identify it, and then I choose the lowest cost cell in that particular row or column. So if I have selected a difference, which means that this is the row that I've selected and I'm going to look at this row or column. So if this is the boxed difference, or this is the highest difference which I have identified, I am going to look at the column which belongs to it. And in that I'm going to try and identify which is the lowest cost cell of that column. So the matrix that is given are minimization, so it has to be the lowest cost. Therefore, the lowest number that is over there, the lowest cost, is what I select, I choose. Then I have an allocation. So I will allocate the maximum possible depending upon the availability and demand. So each row and column have an availability and a demand. So if your rows are availability and columns are demand, or vice versa, whichever is the most possible. So when we do a question, you'll understand this better. But on this step, we allocate the maximum possible depending on the availability and demand in the chosen least cost cell. So the least cost cell that I had identified, I will allocate the maximum possible over there. When the source or destination is fully exhausted, which means it's fully allocated, I cannot allocate anything further over there. I cancel out that row or that column, whichever is fully exhausted. After this, I again go to step 1. I again find out the differences of the two smallest and the second smallest number of each row and column individually, and I repeat all the steps till here. So we redo this entire process till all our allocations are done. In all our allocations, if or in any of these choices, if there is a tie in the highest difference, then we choose the row or column which has the lowest cost cell among the two rows or columns. So if there is a tie between two rows, say for example, so we will see which of the two rows has the least cost cell. If there is still a tie, then we choose on the basis of maximum allocation possible. Even after that, if there is a tie, then we can do any arbitrary selection. So we continue to do this till our allocation, till our availability and supply is exhausted, and then we have to check if the number of allocations is equal to the order of matrix or not. Please note, the order of matrix over here is number of rows plus number of columns minus 1. So whether the number of allocations is equal to number of columns plus number of rows minus 1 or not. If not, then degeneracy arises. So what is degeneracy? We'll cover that a little later in detail, but degeneracy arises if this is not equal. And to remove the degeneracy, a dummy allocation E is to be made in the least cost cell from where loop can't be made. So I have to remove degeneracy. So if my number of allocations is less than the order of the matrix, I have to add a dummy allocation E, which is in the least cost cell where loop can't be made. Before I move on to the next method of IBFS, I want to go through a practical question with you so that you understand really how to implement these steps. So let's look at the question. So this is the question. A compressed natural gas CNG company has 3 plants producing gas and 4 outlets. The cost of transporting gas from different production plants to the outlets, production capacity of each plant and requirement in different outlets is shown in the following cost matrix below. So ABCD are my outlets, XYZ are my plants. From the plants, I have to transport my CNG to the outlets, and capacity of production is given and requirement is given over here. So requirement is demand and capacity of production is availability. So this is what is given, and we have to determine a transportation schedule so that the cost is minimized, and the cost given in the matrix over here is given in thousands of rupees. So this is the question. So what is the first thing that we will do? The first thing that we will do is preliminary check. So to check preliminary, first thing that we do is we check if this is a minimization problem or not. So cost is given over here. So of course it is a minimization problem. So the given problem is a minimization problem. The second check that we do is whether the data is balanced or not. To ensure whether the data is balanced or not, we have to check if the total capacity or the total availability is equal to the total demand or requirement or not. So over here, if you see 700 plus 400 plus 600, capacity of production is 1700 and requirement is 400, 450, 350 and 500, which also totals to 1700. So my requirement is equal to my capacity of production and therefore my data is balanced. So my preliminary checks are done. Now I will move on to IBFS, Initial Basic Feasible Solution, using the Vogel's approximation method, VAM. So the first step of that, if you remember, was to find out the difference between the smallest and the second smallest number in each row and column. So say for example, you consider the first row. So in the first row, if you see, the smallest number is 4, right? The smallest number is 4 and the second smallest number is 6. So the difference between 4 and 6 is 2, which is what I have written over here, right? Then in the next row, the smallest number is 2 and the next number, second smallest number is 3. So the difference between 3 and 2 is 1. In the next row, the smallest number is 3 and so 3 and 5. So the difference is 2 and that is what is written over here. Fine. Now I do the same thing for columns. So in the first column, 3 and 3 both are the smallest numbers and therefore my difference is 3 minus 3 is 0. In the second column it is 5 and 6, so the difference is 1, which is what is written over here. The next one is 2 and 6, which is 4, so I write 4 over here. And in the next one after that it is 5 minus 5, which is 0. So the first row of differences and the first column of differences is what I have derived in the first step. I have to find out the differences for each row and column between the smallest number and the second smallest number. That is what I have done here. Now the second step that I will do is I have to find out the highest difference. So what is the highest difference in these boxes? So if you see in the differences, the highest is 4, right? So I identify this highest difference. So the column that I am going to look at is column C, right? This is the column that I am going to look at. Column C, in column C, I am going to identify the lowest cost cell. So what is the lowest cost cell? It is 2. And over here, I have to allocate the maximum possible over here. So if you see, I have a requirement of 350. How in C, outlet C, but I have a capacity of 400. So I can allocate only 350 because that is the requirement. So I allocate 350 over here, right? When I allocate 350, my requirement of column C becomes 0. So I write column Z over here, 0, and I cancel out this entire column, right? So my column C is exhausted and I do not require that in this anymore. Now I repeat this whole thing again. So I will firstly find out the difference between the column smallest number and the second smallest number. So again, in the smallest number in the first row is 4, second smallest number in the second row is 6. So the difference is 2, which is what is written over here. Then again it becomes, so over here now the smallest number is 3 and the second smallest is 5. So the difference becomes 2. The one after that, again it is 3 and 5 and the difference is 2. Now look at the columns. So in columns, it's 3 and 3, 0 again. 5 and 6, 1 again. This column I will not consider. And column D is again 5 and 5, 0. So now I am looking at the second row of differences and the second column of differences. Over here I have to identify the highest difference. So if you see over here the difference values are 0 and 1 and over here all are 2. So the highest is 2. But I have 3 rows which have 2. So now it's a tie. In the case of a tie, what do? In the case of a tie, we identify the lowest cost cell in the rows of the tie. So I have a tie in all the 3 rows, which means all these cells. and I have to identify which is the lowest cost cell. So if you see over here, the lowest cost cells are 3, which is this or this. So over here, then I have to see what is the maximum possible allocation. So over here, I have already allocated out of 450. 350 I have already allocated. So I only have a 50 allocation possible. But over here, I can allocate 400 because 600 is available and 400 is the requirement. So I can allocate 400. So in this cell, I will allocate 400. Right? So that is what I do over here. Now when I allocate 400, my requirement of A is also exhausted because I have allocated the entire of this. And I had a capacity in Z of 600, which becomes 200 now. So this is 50 now, this is 200 now, this is 700, this is 450, and this is 500 now. Right? Now I repeat this entire process. I will again find the differences between the rows and the columns. So let's do that again. So the first row, the smallest numbers are 6 and 6, so my difference becomes 0. In the second column, my numbers are 5 and 5, so my difference again becomes 0. In the third row, my numbers are 5 and 9, so my difference becomes 4. In the columns, so over here it's again 5 and 6, which is 1, and over here again it's 5 and 5, which is 0. So now what is the highest number in these round of differences? So the third row of differences and the third column of differences. So the highest number is over here again 4. Right? So this is the highest difference. So this is the row that I will be considering, row Z. So I have to see which is the least cost cell. So 5 is the least cost cell out of 5 and 9. And I have to see how much I can allocate maximum over here. So the maximum that I can allocate is 200 because here I have a availability of 200. However, the requirement was 500. But I can allocate only 200 because I have only available 200. So I allocate 200 over here. This is exhausted. I had 200, now it becomes 0. So Z is exhausted for me. And now I am left with over here 300, right? 500 minus 200, 300 is what I'm left with the requirement over here. I have to again redo this process. So what I will do now is, again 6 minus 6 is 0, 5 minus 5 is 0, this is already gone. Over here again it's 5 minus 6, 1, and 5 minus 6, 1. So now I have the highest value as 1 and 1. So again this is a tie. I have to see which is the least cost cell. So over here the least cost cell is 5 and 5. So now I have to see what is the maximum possible allocation. So if you see, in both of them only 50 is possible because over here I have 50. Here although I have 450, here I have 300, but then there is no other option. I cannot allocate more than 50 in either of the two cells. So I have to make an arbitrary selection. So I select this and I allocate 50 over here, right? So now I'm left with nothing on this row as well. So this is also exhausted. So now what am I left with? Do I really need to do it again? I can allocate this very easily. So whatever I'm left with now, I will have to allocate 400 over here. And I'm left with 300 over here, which I will have to allocate over here. 700 was the capacity and it ties properly. Right? So this is the allocation that I have got. 400, so 400 in B, so outlet B, production X, 400, production X, outlet D, 300, Y and B 50, Y and C 350, Z and A 400, and Z and D 200. So these are the allocations. The next step that I have to do is I have to check whether the number of allocations is equal to the order of matrix or not. What is the number of allocations here? I have 1, 2, 3, 4, 5, 6 over here. And what is the order of matrix over here? Number of rows is 3, number of columns is 4. So 3 plus 4 minus 1 is 6. And I have 6 allocations over here. So therefore my problem is not degenerate and I do not have to add a value E. So that is, so number of allocation is 6. Order of matrix is 3 plus 4 minus 1 equal to 6, and hence the problem is degenerate. So once you finish step 2 and you find out the IBFS, we have to do an optimality test. We will come to the optimality test of this question later. let's get back to our concepts. So I think with this example, the Vogel's approximation method should be clear to you by now. Now let's look at the other two methods that were part of the IBFS. So initial basic feasible solution could have been solved in three methods. The first was Vogel's approximation method, the second was the northwest corner rule, and the third is the least cost cell method. Let's look at the northwest corner rule. So the first thing that is written over there is that optimality test, which is the step 3 of a transportation problem, cannot be done if you're using a northwest corner rule. Now what is a northwest corner rule? I begin from the northwest corner of the matrix. So if this is my matrix, right, this is my matrix, I start from the northwest corner of the matrix. So this is north and this is west, right? So I start from the northwest corner, which is this cell. I start from this corner of the matrix and I allocate the maximum possible depending on the availability and demand. I just go on allocating based on the maximum possible that I can allocate from the northwest corner. Like earlier, one row and column will keep getting cancelled out. The source or the destination or the availability or the requirement will keep getting cancelled out as and when I exhaust them. So that is the first and the most important step of northwest corner rule. The second is we move on to allocate the maximum possible in the northwest corner cell of the remaining matrix and continue to move in the same manner. So once I have done it in this cell, either this row will get cancelled out or the column will get cancelled out. If I cancel out this row, then I am left with this matrix. So what is the northwest corner cell of this? Which is this. So I will allocate it here. Now if I do this and this is getting exhausted, then I will do it here. And so on, I will continue to allocate my numbers, the most maximum possible, until I'm exhausted with everything. So that is northwest corner rule. Now what is the lowest cost cell method? As you can very well understand from the name, lowest cost cell method is we begin with the least cost cell and we allocate the maximum possible in that cell based on the availability and the demand, and we move on to allocate it in that same. So we begin with the least cost, we allocate the maximum possible in that cell. Whichever source or destination is exhausted, we cancel that out. Out of the remaining, again, which is the least cost cell, we do the same thing again. So we move on to allocate the maximum possible in the lowest cost cell of the remaining matrix and continue to move in the same manner. If we have a tie, then we do an arbitrary selection. So those are the three methods of initial basic feasible solution, or IBFS, which is Vogel's approximation method, northwest corner rule method, and the lowest cost cell method. So the other two, the second two, the northwest corner rule and the least cost cell method, are pretty easy to understand, and that is why mostly what is required in the exam is the Vogel's approximation method. It is very rarely that these other two methods are asked for in the exam. After this, we come to the optimality test. So what is the optimality test? So in optimality test, we have to draw three tables. Okay. To understand these three tables, we must understand the figure that is shown over here. So what is it that is shown over here? So the box, the black lines that you see, this is your matrix. Okay. The C written inside are the elements or the cost cells inside the matrix. So that is all that is the matrix. C values, the cost values of the matrix. The U's are nothing but what is written on the side of the rows, and V's are nothing but what is written below the columns. And the equation over here is U plus V is equal to C. So this U and this V, when we add this, should be equal to this C. So I hope you understand this equation very well, because this is what we are going to use in the next three tables to be able to understand the optimality test. So U plus V will be equal to C. That is what this is all about. Table 1. In table 1, we are to find U and V from the allocated cell elements. So the allocations are done. If you remember the example that we did, there were 6 allocations, and there were cost cells in each allocation. So based on those cost cells, we have to derive the U and V. Now you will ask, how will we do that? So you write down the matrix with the cost cells of the allocated positions, and you begin with any one U or V as 0, and you similarly compute the others. Then we write the cell elements of allocated cells, table, row, column with maximum allocation as base 0, any other row or column if required. And then we get the U and V from the equation C is equal to U plus V. Table 2, we are to find C for the unallocated cells. So now we have U and V, we just have to add the 2 and write it in the unallocated cells. So write U and V from the, table 1, fill values in unallocated cells with the help of this equation. So we add the 2 and we fill the values of C in the unallocated cells. Table 3. Table 3 is the actual cost cell minus U plus V for unallocated cells. So we take the actual cost and we deduct the values that we derived in table 2 for the unallocated cells. So deduct values of table 2 from the original cost elements. Now if all values are 0 or positive, IBFS is optimum. So in table 3, if all my values are 0 or positive, then IBFS is optimum. If any value is negative, then it is not optimum, and we have to use loop matrix to be able to get an alternate solution, if to be able to get an optimum solution. If we have 0, then it only means that we have alternate solutions, and the number of alternate solutions will be number of zeros plus 1. So that is the optimality test. Let's just, before we go on to loop matrix, let's just see the optimality test on the example that we did. So this is the IBFS that we created, and there were these 6 allocations that we did. So the allocation cells, the cost cells, if you see, are 6, 6, 5, 2, 3, 5, right? Sorry. So this is the first test. This is the first table of the optimality test out of the 3 tables, and we have copied the cells, the cost values of the allocated cells 6, 6, 5, 2, 3, 5, and from this we are going to be able to derive the U and V. So we see the maximum allocation. So if you see, the maximum allocation was over here 400. 400 is either column A or B, so you can begin with any one as 0. So since the cost cell was 6, I start with that, I put that as 0. So the corresponding U, so V is 0 over here, so the corresponding U can be 6. I mean, it will be 6. So 0 plus 6 will be equal to 6. So that is how I compute. Now that I have 6 over there, there is another 6. So this 6 will, obviously the V over here will become 0. 0 plus 6 is 6. Then over here, I have already put 0. So then this number will be 5, right? If this is 5, then this is 3. So this will be minus 2. So that, and if this is 0 and this was 5, then this was obviously 5, and if this was 5, then this is 2 and this becomes minus 3. Minus 3 plus 5 is 2. So this is how we derive this table with on the basis of U plus V, and that is table 1. Now let's look at table 2. So in table 2, we have to find out U plus V for the unallocated cells. So I cross out all my allocated cells. All the crosses that you see are my allocated cells. So I'm not going to look at that. I'm only going to look at the others. So if you see my first cell is 6 and minus 2. So this is minus 4. So this becomes 4. On this cell, 6 and minus 3, this becomes 3. 5 and minus 2 becomes 3. 5 plus 0 becomes 5. 5 plus 0 is 5. And 5 minus 3 is 2. So this is how you get U plus V for unallocated cells in table 2. So this is table 2, and this is how you derive table 2. Now the table 3 of the optimality test is what we have to do is we have to deduct these values from the actual costs in the original matrix. So in the original matrix, if you see, it was 4 and 8 in the first row, right? So here I have 4 and 4, so, and this is 8 minus 3, so 5. So it should be 0 and 3, alright? So that is what I have. Then I have 3 and 5. So just by deriving that, this is what I'm getting. So this is the matrix that I will get by deducting the table 2 values from the actual cost values in the original matrix for the unallocated cells. Now if you see over here, all my values are either 0 or positive, and therefore this solution is optimal. This initial solution is optimal since all the values are positive or 0. So however, like we said, if zeros exist, then there is an alternate solution. Since there are 2 zeros, there are 3 optimal solutions possible. Number of zeros plus 1. So there are 3 alternate solutions possible. So we come to that later. Let's just go back to our concepts. There was a concept of a loop matrix. So if your solution is not optimum, then you have to use a loop matrix. So what is a loop matrix? Loop matrix is used to find alternate solutions. It is also used to find optimum solution when optimality test fails. When we get a negative value in table 3 of the optimality test. What are the steps of the loop matrix? We have to draw a loop beginning from the cell where allocation is to be done. 0 value or negative value. So if it is a failed optimality test, then we will use the negative value from where the allocation is to be done, and from there we will draw a loop. If it is an alternate solution that we are trying to find, then from the 0 we will draw a loop. We will turn only where the allocations are done, and the loop should only be a rectangular or the square. So there should only be 4 arms to the loop. Then we write plus and minus alternatively at the turns or corners of the loop. Where the allocation is to be done, that negative value or 0, where we had started from, over there it should always be plus, because you were going to allocate over there. So it has to be plus. Then among the cells, where cells signs have been placed, lowest allocation is added or subtracted to get new allocation. So out of the pluses and minuses, all of the 4, whichever is the smallest allocation is what we add and subtract in all of them. The new allocation becomes the new solution derived by the loop matrix. And optimality test is again to be redone if the test had failed earlier. If it's an alternate solution, then you need not do it. But if it was not the optimal solution earlier and you were trying to find the optimal solution, then the optimality test will have to be done. So if you remember in the problem or in the example that we were solving, we had zeros and we said that there are 3 alternate solutions possible. So using this loop matrix, let's try to find out the alternate solution. So yes, so we had zeros over here and therefore alternate solution is possible. So this is first and foremost this, okay, let's just come to this. So some values in table 3 were 0 and therefore the above solution was not unique and alternate solutions exist, and we are going to find the loop matrix. So if you see over here, what I did was in this loop matrix, I have put down the allocations that were done. 400, 350, 50, 400 and 200. These were the initial allocations, okay. This was this, and this. These were the initial allocations. Now, I had a 0 value. Where did I have a 0 value in the question? So I have to allocate over here. So from here I will start the loop. And to start the loop, what I will do is I will draw it. Sorry. From here I will start the loop and I will turn my loop at the places where I had allocated. So these were my allocations. This is my loop. Now at the corners of the loop, I am going to write plus and minus alternatively. I have to write a plus where I have to allocate. So this becomes a plus, this becomes a minus, this becomes a plus, and this becomes a minus, right? So these are the pluses and the minuses that I write at the corners of the allocations. Now, the lowest of these allocations is the number that I have to write. So 50 is the lowest allocation of these 4 allocations. So I write plus 50 here, minus 50 here, plus 50 here, and another minus 50 here. So this becomes 50, 0, 450, 250, and 200 and 400 remain the same. So that is the alternate solution or the revised allocation. So just before we go back to the concepts, let's just close out this question. So this is the optimal transportation schedule that we prepared as per this chart. 400, 350, 350, 400 and 200 allocations, 6 allocations. That is the 6 allocations that are listed down over here. From plant X to outlet B, 400 units at a cost of 6, total cost is 2400. Doing this, we get the entire table. We get the total cost 7,350,000, which means 73,50,000 is the minimum cost of transportation based on this optimal transportation schedule. However, I have an alternate solution, and that alternate solution was what I found out by the loop matrix over here. And this is the alternate solution of that. So the only few things that change is X to B instead of 400 becomes 450, and X to D instead of 300 becomes 250, and so on. The costs will change, but the total cost still remains the same, 7350 or 73,50,000, because it's just an alternate solution, the optimal solution but an alternate solution. So that is the alternate transportation schedule. So with this was the example that we were discussing on transportation. Let's just go back to the concepts. So we had done the optimality test. It had passed earlier, so we were not required to do it again because we were only finding the alternate solution. However, if the test had failed, then after the loop matrix we would have to do the optimality test again. So there are 2 other concepts which we should know in transportation. One is prohibited routes and the second is degeneracy. Degeneracy is something which we discussed during the course of doing it. If the number of allocations was less than the order of matrix, then the problem was degenerate, and we had to insert a dummy allocation E from where the loop could not be made. So let's just do degeneracy first. So what is degeneracy in a transportation problem? If an IBFS with M origins and N destinations has fewer than M plus N minus 1 positive allocations, so this is nothing but the order of the matrix. So if my allocations in the IBFS is lesser than the order of the matrix, then the problem is said to be degenerate transportation problem. Such a situation is handled by introducing a dummy allocation E in the least cost and independent cell. So that is what is, if you degeneracy in a transportation problem comes often for a short note in the exam. So if it comes, please make sure you are able to write this easily, because there's really not much to understand and know in this. This is what is degeneracy. So please be prepared to write a short note if it comes in the exam. The other concept which I wanted to talk about is the prohibited routes. Now what are prohibited routes? Prohibited routes is an option or a route which is not possible or which is very difficult. So it's a not possible or a very difficult option which is denoted by M, and the value is very close to infinity. So a prohibited route is a difficult or impossible option denoted by M, and the value of which is very close to infinity. So with that we come to the end of transportation. We covered what is transportation, we covered the steps of transportation, preliminary check, IBFS, optimality test, the 3 methods of IBFS, Vogel's approximation method or VAM, northwest corner rule method, lowest cost cell method. Then we understood we looked at a practical example of how to find out the VAM, IBFS, optimality test. If there is an alternate solution, or if the test fails, then we have to do an we have to find out another solution using the loop matrix. So we did all of that, and how to prepare the transportation schedule after it. So that is all what transportation talks about, and I hope you did understand this well, and I hope you will go back and practice a few more questions based on this lecture to be able to understand it better. Thank you.